Hi, welcome to this video session. In this series of videos, we are going to discuss about the various process takes place in the air standard cycle. Air standard cycle is one of the important topic in the applied thermodynamics. To name applied thermodynamics, the name itself explains that it is the application of the thermodynamics principle which we had studied or we had discussed during the basic thermodynamics classes. It is one of the interesting subject where everyone can score very good mark. Under air standard cycle, various cycles comes and we see the working principle of each and every cycle in the set of videos. First, we start with Carnot cycle efficiency explanation. Before that, we should know what is air standard cycle. Air standard cycle is a thermodynamic cycle where where a system undergoes various processes and come back to the initial states where it starts. It is a thermodynamic cycle, and when you use air as the working medium in this thermodynamic cycle is called as air standard cycle. And we need to assume certain things in air standard cycle. The main assumption are the working medium which we are using in the air standard cycle are perfect gas, particularly air, and there is no chemical reaction occur during this cycle, and all the processes are reversible process, and we need to assume that there is no heat transfer takes place from the system and the surrounding. That means whatever heat supplied into the system is completely converted into useful work. That gives, or in other words, it should produce 100% efficient engine. Is it possible? Definitely not. There is a reason we call this a cycle as ideal cycle, and we keep these cycles as a reference to compare with the actual cycles. Now, let us see how Carnot cycle works and how the Carnot cycle efficiency are carried out or derived. Carnot cycle occurs with 4 processes. It has 2 isothermal processes and 2 adiabatic processes. The main thing we need to note here is the heat addition takes place when expansion when the process is adiabatic or the temperature remains constant, and heat rejection also takes place when the temperature remains constant, and moreover all the processes are reversible processes. Since it is a reversible process, every reversible process are known as isentropic process. That means entropy remains constant. When you observe in the temperature entropy diagram, you can see the process 1 to 2 is where the entropy remains constant. This is reversible isentropic process. Reversible adiabatic process, and here the temperature remains constant, and we are adding heat to this. We call this as a maximum temperature, where heat is rejected to the sink is called as lower temperature. The working and efficiency of the Carnot cycle can be clearly explained in this video. Do observe this video. It will give clarity about Carnot cycle efficiency calculation. Let's watch these videos first.
2 diagram. One is the pressure versus volume, and second diagram, that is the temperature versus entropy. So this is the engine cylinder, and this one is the one end of the engine cylinder, and inside the engine cylinder this one is the piston. So the piston will reciprocate inside this engine cylinder, and this is the insulator that is initially covered over here at the end of the engine cylinder. This is the heat source having temperature T1, and this is the heat sink having temperature T2, and obviously you know that T1 is greater than T2. So initially insulator is uncovered at the end of the engine cylinder, and so that heat will supplied from the heat source to the working fluid, or you can say working substance that is available over here. Generally for the Carnot cycle, it is the air and that air is the perfect gas. Due to the application of the heat from the heat source, the air will expand, and so that the piston will move from left to right side, and that movement, that is called as the initial stroke. And I am going to draw the same stroke in pressure versus volume diagram and temperature versus entropy diagram. So let's say it is the initial condition at this point is 1, and this is second condition of the air, and this will be the stroke, or you can say the process 1 to 2. And this process on the TS diagram, that means temperature versus entropy diagram, it is the horizontal line 1 to 2. So I can say during the process 1 to 2, that is isothermal expansion, and that you can see at the constant temperature the volume is increased from V1 to V2. So this is called as the expansion. So 1-2 process is called as the isothermal expansion. The heat source is in contact with the cylinder, that you can see from here. The air expands at constant temperature, that you can see over here at constant temperature, and so that the volume is increased from V1 to V2. So here you can say that volume is V1 and here it is V2. So the volume is increased from V1 to V2, and during this process heat is supplied from the heat source. Let's say it is Q1. So this is at constant temperature T1 and the heat is supplied, that is Q1. Now that heat supplied is removed and that is covered with the insulator. Now again piston will move from left to right, and that stroke or that process is represented by 2-3 on the PV diagram, and here it is also 2-3 on the TS diagram. The process 2-3, that is called as the adiabatic expansion. Here you can see the volume is increased, so it is expansion, and during that process entropy will remain constant, so that it is called as the adiabatic process. So during adiabatic process entropy is always constant. So the heat source is removed over here, you can see, and insulator is covered at cylinder end. Air expand with reversible adiabatic process. So during reversible adiabatic process volume is increased from V2 to V3, and you know that during adiabatic process no heat is transferred. Now this insulator is once again uncovered, and now piston will move from right to left, and during that heat is rejected from the working fluid to heat sink. And this process on the PV diagram is like this, on the TS diagram is like this. 3-4, that is called as the isothermal compression. So isothermal means you can see over here at constant temperature. Compression, so the volume is decreased from V3 to V4. So the insulating cover is removed, heat sink is connected with the cylinder end, air is compressed at constant temperature, and hence volume is reduced from V3 to V4. So that is at constant temperature T2, and during this process the heat is rejected from the working fluid to heat sink. Let's say it is Q2. Now next, once again that insulator is covered, and so that no heat will be transferred. Piston will move again from right to left, that means the initial position of the piston at state 1. So that process is represented by 4-1 on the PV diagram and on the TS diagram. So 4-1 is the adiabatic compression. Here you can see the volume is decreased, that's why it is compression. During that, entropy is constant, that's why it is called as the adiabatic process. So the heat sink is removed and insulator is covered at cylinder end. Air is compressed with reversible adiabatic process. So in the reversible adiabatic process, entropy is constant always, and here you can see the volume is decreased from V4 to V1, and always during adiabatic process no heat is transferred. So here I can say these both processes are the adiabatic process, and during that adiabatic process entropy is constant, no heat is transferred. And these two processes are the isothermal process, and during isothermal process heat is transferred. So this is the summary that we have discussed during process 1, 2, 2, 3, 3, 4 and 4, 1. Now efficiency of Carnot cycle. So as we have discussed these two diagrams, PV and TS diagram. Now during process 1, 2, heat is supplied and that is exactly equal to the work done by air. So I can write over here Q1 that is equal to W12. That means whatever it may be the heat supplied, that is converted into work done, because of it is isothermal process. And as you know that according to first law of thermodynamics, heat supplied is completely converted into work done during isothermal process. So this is the heat supplied Q1 and this is the work done during process 1, 2. And you know that for the isothermal process it is equal to P1 V1 ln V2 by V1, and that V2 by V1 that is called as the expansion ratio. So I can say P1 V1 is equal to mRT1 as characteristic gas equation, and V2 by V1 that is the expansion ratio R. Let's say it is equation number 1. Now during the process 3, 4, heat rejected, and that is once again at constant temperature, so that heat is exactly equal to work done. But here this heat is rejected, and that's why work done that is on air, over here work done by the air, because of it is the heat supplied. So it is plus sign, over here it is rejected, so having minus sign. So I can say it is minus work done during the process 3, 4. And so that you can understand the work done that is equal to P3 V3 ln V4 by V3. Keep in mind that during this process, this V2 is your final volume and V1 is your initial volume. So it is final volume upon initial volume. Similarly over here it is final volume upon initial volume. So you can see 3, 4, this is your final volume and this is your initial volume. So if I want to convert this negative sign into positive sign, then I can say it is P3 V3 V3 by V4, and that V3 by V4 that is the compression ratio. And as you know that for the closed cycle, expansion ratio and compression ratio are always equal. P3 V3 that is mRT, and that is at temperature T2, so I can say it is mRT2, and this is the compression ratio, and so that I can say it is ln R. So keep in mind that for the closed cycle, and Carnot cycle is the closed cycle, so we can say expansion ratio and compression ratio are equal. That means V2 by V1 is equal to V3 by V4. Let's say it is equation number 2. This is my next page and this one is the earlier page. So W net is equal to Q1 minus Q2. That means the net work done during the Carnot cycle. And you know that efficiency of Carnot cycle is equal to output upon input. And here output is the net work done, that is Q1 minus Q2. And input, you can see from the cycle, your input is what? Q1. So W net is equal to Q1 minus Q2. So I can put it over here upon Q1 as it is. So if I simplify further, then it is Q1 by Q1 minus Q2 by Q1. And so that it is 1 minus Q2 by Q1. So let's say it is equation number 3. Now this is my earlier page. So efficiency of Carnot cycle that is equal to 1 minus Q2, and Q2 is equal to mRT2 ln R upon Q1, and Q1 that already we have derived, Mr T1 ln R. So here Mr will be cancelled, ln R will be cancelled, so that your remaining term for the efficiency of Carnot cycle is equal to 1 minus T2 by T1, and that is the efficiency of Carnot cycle. Let's say it is equation number 4. So from this equation number 4 you can conclude that the efficiency of Carnot cycle depends only the temperature T2 and T1. That means the temperatures of heat source and heat sink only. It is not depend on the working fluid. So thanks my dear friend. Two diagram. One.
To summarize this, the derivation of Carnot cycle is as simple as is explained in this previous video, and it's easy for us to understand as well. And the main point which we need to recollect at this point is there are 4 cycles, 4 processes are happening in this Carnot cycle. Okay, 2 are isothermal process and 2 are adiabatic process, and all these 4 processes are reversible process, since we assume this as a ideal processes. And reversible adiabatic process is also known as isentropic process. And the efficiency of the Carnot cycle is completely depends upon the lower temperature as well as the higher temperature. It doesn't depends upon any working medium. That's it guys. Now let us find out in this video, and in next video we will see about how Carnot cycle works. Thank you. Bye. Cheers.